Okay, good. Thank you very much for the opportunity to give a presentation here at the very auspicious beginning of this this new institute. I'm very happy to be introduced by Yong-Baek Kang, who is one of my co-authors. Right. And I'm also very happy to see so many familiar faces from the IMA, including a former postdoc who is now here, Dr. Hyun. Okay, so what I will do today is give a little presentation about the history of the IMA, how it started, and what we're doing now, and how the outreach to industry has been created, and how we maintain this relationship with industry. So the IMA's origin is from the 1979 United States National Science Foundation called, wow, is it because of, am I too close to this, right? Okay, I'll stand on this side, sorry. It was a National Science Foundation call for proposal for establishment. In fact, the call for proposal said A, Mathematical Science Research Institute. And you notice that Mathematical Science Research Institute stands for MSRI. So they established at least one, but in fact they only had the intention of establishing one, and IMA had a very unusual proposal that they liked so much that they actually established two, even though they initially intended to establish one. The rationale in this call for proposal is as follows. American research in mathematics today is in a golden age, but there is within the mathematical community a general consensus that in order to maintain and even further stimulate the unequal pace of research in the past dozen years, another mathematical science research institute similar to but not identical to the famous Institute for Advanced Study should be established. So they were using the Institute for Advanced Studies School of Mathematics as a model. And they thought that there should be another one like that for the math community in the United States. By the term Research Institute, we mean an organization where mathematical scientists on leave from their home institutions of permanent employment can congregate in appropriate numbers for extended periods for the sole purpose of performing research. And the aim of the institute is, of course, the promotion of research in the mathematical sciences. So it was a very important call for such an establishment of such an institute, and I'm very happy to see that this idea, this model has been adopted in many places, including Korea. The IMA proposal was very unusual in the following sense. It was written by Hans Weinberger, a specialist in PDEs, Willard Miller, a group theorist, and George Sell, also in PDE. They responded, it was an interesting proposal in the sense that it responded to the isolation of the growth in mathematics, not only from each other, but also from other disciplines. What they were seeing at that time in 1979 was that mathematics was becoming isolated by itself from the other sciences, but also within mathematics itself we were building walls. The topologists were not talking to the number theorists were not talking to people in PDEs, and so on and so on. So their idea was that those walls have to all come down. So the line that came in, that I copied from the proposal, was the historical linkage between mathematics and the sciences, which has been of such great mutual benefit in the past, is in need of nurture. So they put forward a very forward-looking proposal which repudiates the artificial boundary between pure and applied mathematics. They want to engage scientists and engineers and those from industry. And they want to encourage application of mathematics by engaging mathematicians from the core areas of mathematics. So it's not just an institute for people who are already doing applied mathematics, but they want to draw other people into this institute to work on problems coming out from other fields, because in the process it enriches the field of mathematics, not only just the field that mathematics touches upon. This idea was very forward-looking, and in fact they didn't use this word, interdisciplinary research. This is a new word that has been coined in the last 30 or 35 years or so, and I think the IMA has a lot of credit to pushing this idea. The idea of mathematics being a part of a discipline that develops a new field. So the major objectives, this is again taken from the proposal, to encourage development and the study of fresh mathematical concepts and questions which are of concern to other sciences, to bring together mathematicians and scientists from diverse fields in an atmosphere that will stimulate substantial collaborative efforts, to facilitate the solution of major outstanding problems in various areas of mathematics. And the way that they were going to do this is by creating what they call a yearly program. A yearly program is devoted to studying the possible interaction of mathematics with a specific area of science. Scientists with common interests are invited to be in residence at the IMA for sufficiently long periods of time to allow interest in the non-trivial problems which arise to grow and familiarity to develop. Workshops provide periods of intensive activity and involve a larger segment of the industrial, academic, and governmental scientific community. So even then, they were already talking about reaching out outside of academia, at the universities, to industry and to government labs. There was already support from industry from the very beginning. In the proposal, there were 4 letters of support from 4 companies that were located in Minnesota at that time. There were Honeywell, 3M, Control Data, which no longer exists, and Cray Research, which is the supercomputing company that was established in Minnesota. When IMA was formed in 1982, we formed an industrial advisory board. So the IMA today, so we are still sticking to the same mission. Our vision is to be the world's premier mathematics institute where diverse talents address core challenges in science, industry, and society. I put a couple pictures here for a good reason, because we're touching on young people in terms of training them to do this kind of mathematics where they address problems from other fields. We also engage the highest quality mathematicians to be and scientists to be part of the organization of meetings and activities. Here you see a picture of Pierre-Louis Lyons giving a talk about mean field games, and this is one of our program organizers from 2007. If you recognize him, it's Michael Levitt, who won the Nobel Prize this year in chemistry. In fact, there have been 2 Nobel Prize winners as organizers of IMA programs. The mission statement is the same. It encapsulates what I've mentioned before from our proposal. The Institute for Mathematics and its Applications connects scientists, engineers, and mathematicians in order to address scientific and technological challenges in a collaborative, engaging environment, developing transformative new mathematics and exploring its applications while training the next generations of researchers and educators. So the annual thematic program has grown quite a lot since the very beginning, which was 32 years ago. We now have typically between 45 researchers in residence at any given time, including 15 postdocs. We have 6 to 7 thematic workshops that are around the thematic year, topics of the thematic year, each drawing an additional 80 to 100 participants. Workshops have very few talks. Interactions among participants is highly valued. So if you look at the end of the year, when we do the statistics of how many people actually comes to the IMA and how many actually gives talk, it's about 20%. The ability to come to the IMA and to come to an institute like CAMP is the fact that you are exposed to all these ideas, to all these people, and the value is from the interaction. The talks are there mostly to inspire, to generate conversation. So very few people give talks, and they don't mind the fact that they don't give talks at the IMA, because being there is so highly valued. We also, when there are no workshops, because we have a critical mass of number of people, they organize their own tutorials, short courses around the topic of the thematic year. They form study groups on the theme offered during the year. At the end of the year, we collect information about what they accomplish, and then 3 years later, we continue to follow what they do. This process has actually successfully launched very cohesive community of mathematicians that didn't exist before these programs were created at the IMA. Here are the thematic programs from the last couple of years and what's going on now. It's always on an area of application and all the mathematics that supports it, or on a mathematical area and all the different applications that come in that area, in that mathematical topic. So we had the mathematics of information in 2011 and 12. So we were already addressing big data before big data was a big buzzword. Infinite dimensional and stochastic dynamical systems last year. And this year, a very innovative program focused around using algebraic topology to address scientific and engineering applications. Next year will be discrete structures, analysis and applications, and then the year after that, control theory and its applications. We plan things 3 or 4 years in advance because we need to have that time to gather the community together, to get them excited about the program, to make them commit to come to the IMA and so on. There are other activities that we do. We also run workshops, hot topics and special workshops. I'll talk a little bit about those in a minute. And then I'm going to definitely talk about industrial postdoctoral fellowships. And also this one, mathematical modeling in industry workshops. We also have a new directions program in which we invite professors who are on sabbatical to come and immerse themselves in the topic of the year. And then we also offer short courses in June for people in mid-career who want to learn about a new subject area where they have a potential to contribute as a research topic. We also provide interdisciplinary research experience for undergraduate. This is a joint program with Macalester College. And we have participating institution programs, which includes conferences and summer schools for the participating institutions. And recently we created an agreement with the Norwegian Academy of Science and Letters, and we have been hosting the Abel conferences, which celebrates the Abel Prize winners. We're also gearing up our effort, and I'm very happy to be here because we're trying to do a lot more in international outreach, and I hope that by the end of this week we will have some ideas about what we can do with Korea. So in a typical year, we have over 1,000 visitors to the IMA. So industrial partnerships. So this program was created many years ago, participating cooperation program. A participating cooperation pays a membership fee. The benefits include opportunity to hire industrial postdoc, provide input on scientific programs, special funds to visit the IMA that they can have control over. They can have a chance to mentor graduate students in this workshop. And at the moment, we have 11 companies that have been with us for quite a while: Boeing, Corning, Eaton, ExxonMobil, Ford Motor Company, General Motors, Honeywell, IBM, Medtronic. This is a medical device company. Schlumberger Doll Research, which is an oil services company, Schlumberger, and Siemens in Germany, based in Germany. Honeywell has been with us since the very beginning, since 1982. The industrial programs involve the following aspects: industrial participants at our annual programs, industrial advisory board. They provide advice to us and suggest ideas and topics for our programs. We have an industrial postdoctoral program, which I will discuss in more detail. And then we have this workshop, mathematical modeling and industry workshops, which I will describe also in more detail. And then we also have hot topics workshop with ideas that originate from industry. And then we also have finally this industrial problem seminar where we invite scientists from industry to come in for a short visit, 1 or 2 days, to give a talk at the IMA on the kind of work that they do and the kind of mathematics that is used in their research. Oops. So industrial postdoc program is jointly funded with a company, with the PC. Half of the effort is on the company project, half the effort on their own research. So the postdoc can usually apply, and they choose a project that they work with a company, and then the other half of their effort is on their own research, so they can continue to develop independent research while they are working with this company project. It's a 2-year appointment. If a company is far away, 1 year at the company and 1 year at the IMA. But if they're nearby, they would spend a few days at the IMA and a few days a week at the company site. We assign mentors at both places. This is very important because you want to make sure that the postdoc has somebody who's interested in their career as well as in the research product that they produce at the company. But also somebody back in the university that could also advise them on careers and also on research topics that they might want to be pursuing. Selection is based on qualification and background for the project. So over 60 industrial postdocs since 1988, about half of them have ended up in industry, the rest at the universities. Many sponsoring companies value the program for its ability to recruit talented mathematicians. Some of them have hired these postdocs immediately after they finished their postdocs with us. Most companies say that the postdocs provided valuable research that contributed to the R&D of the company. A few of them actually gave us an estimate of the dollar value of the contribution of the postdocs to the company. There was one company, Honeywell, that actually spun off a company that was worth several hundred millions, and they felt that a lot of what the technology that was able to create this company was created by the work of the postdocs. I will now give some examples of projects that we've worked on with industry. The first one is modeling ablation therapy. This is a therapy that is used by doctors to prevent, to help patients with irregular heart rhythm. In ablation therapy, a doctor uses a tool to basically to destroy cells in the heart that are responsible for irregular electrical wave patterns. The tool generates heat in the tissue by Joule heating, and irrigation at the contact site helps control the heat. So you want to control this in such a way that you want to be able to get the temperature high enough to damage, to kill the cells, but not too high that you actually destroy the integrity of the structure. So this is an example of some of the tools that they have from this company, Medtronic. So basically, this tool is used, is applied. In this case, this would be used by pinching the tissue. In this one, you just use it by contact. This is the kind that our postdoc model. So the mentor there was David Franciscelli, and the postdoc was Jay Gopalakrishnan, who is now at Portland State. So Jay developed a 3D model which couples electrical field with heat conduction, and then he developed a new boundary condition which models the irrigation process. So this is from the paper that he published. You can see here, this is the heart tissue. This is the probe, the electrical probe that generates the heat inside this tissue. Blood is flowing here, so it also takes away some heat. And then there's the irrigation here, which also controls the heat that's being produced there. So he modeled this with a three-dimensional, full Maxwell's equation, and then he has the Joule heating in the tissue. And here's a temperature profile that he produced from his simulation. You can see that there's the heated section, and this part is being advected away by the blood flow inside the heart tissue. The outcome: Jay got a major publication out of the work and a contract to do more work after he left the IMA. Medtronic was able to use his computational tool to design new instruments, some of which have been marketed in the last few years. The other one I want to talk about is the modeling of dense particulate flow. This is a project with Corning. Many manufacturing processes require the extrusion of a thick fluid with dense particulate hard suspensions. It's like a composite material in the matrix. And success in manufacturing depends on controlling the flow. An accurate simulation tool is desirable so that engineers can perform what-if experiments without going to the laboratory. So you can use the simulation as a way to design a process. So this is a micrograph of a typical extrusion at Corning. You can see there's small particles as well as larger particles, and this is all embedded inside a fluid that's being pushed. So what did the postdoc do? So the postdoc was Wei-Gang Zhang, and the mentor was Amy Robelset. Wei-Gang developed a fluid, he modeled the fluid using Navier-Stokes equation and introduced hard particles of arbitrary shapes that can collide. Using the method of immersed boundary of Peskin, he was able to track the particles in the flow as they interact with each other and the boundaries. So the outcome: Wei-Gang got a valuable industry experience that led him to a job with Oracle. That's where he's working now. And Corning scientists learn new computational methods that they now use in other problems that they work on. The other thing I want to talk about, the other program, is Math Modeling in Industry Workshop. This is something that I think will be very appropriate for an organization like CAMP. It's a program in which an industry scientist poses a problem and mentors a team of 6 students as they work to solve the problem in 10 days. So they have 10 days. They don't come in there to see the problem cold, but the problem is actually posted on our website first, and the student can choose to work on this problem. But most of them, they just basically read the background material, and then they show up and they start to work together. We typically run this annual program with 5 to 7 projects, depending on the number of projects that we have from industry and number of and where we hold it. So the next one is going to be at University of British Columbia campus. So if you have students who are interested in participating, please let them know about this. We have had participants from KAISP in the past. So this is a very exciting program because the students get to have ownership of a new project, and they get to work in a team environment to solve this problem. So I want to give you a sample project. This is a project that was proposed by Michael Hofmeister from Siemens. The project title was Planning a Water Supply Network. So you're given a network of water supply consisting of sources, reservoirs, and pumps, and a water demand schedule. You want to find an optimal way of meeting the demand which minimizes the cost of switching the pumps on and off. So additionally, there are constraints on the flow rates and the starting and ending condition on the reservoir level. So you don't want to drain one reservoir too much. You don't want to overfill one reservoir too much. So you have to control these things. So this is from the report, actually. So you have, this is a well, this is a stream, these are the reservoirs, and these are the pumps. And this is the supply that's being controlled. Okay. And what did the students do? The students formulated an assignment problem which amounts to a mixed integer programming problem. They used an existing public domain software to solve the problem. They only had 10 days. They couldn't write all the codes in the world, right? They gave a progress report 5 days into the project, and the final presentation and a written report. And the written report is actually available on our website. Many of the reports are. Outcomes. So for many of the students, it was the first time they work in a team. A lot of mathematics is even today is done as an individual sport. It's not a team sport. And in this case, we formed teams, and they worked on real-world problems. And this was a very good experience for them. The experience also gave them an idea of how mathematics is used to solve industrial problems. So they realized and appreciate the utility of mathematics on real-world problems. For the mentor, it was a chance to work with bright and hard-working students. Some his company might want to hire. In fact, several of our previous projects with students have resulted in students getting jobs in the company after the program. The added bonus was that in this particular case was that the team discovered aspects of the problem that the mentor was unaware of. So he was actually discovering a phenomenon that even though he was an expert in this field, he was not aware of. I also finally want to mention a little bit about the industry-motivated workshops. There's the medical device biological interaction. So these are workshops that are suggested by our industry partners. This was suggested by Medtronic. They were interested in the interaction between medical device and biological tissues at the material tissue interface. We have also antithesis quantification in industrial and energy applications. This was a workshop that was suggested by Siemens. This was a workshop that was suggested by IBM, Mathematical and Computational Challenges in the Control, Optimization, and Design of Energy-Efficient Buildings. And this one was suggested by, actually by the National Geospatial Intelligence Agency, Imaging in Geospatial Applications. In a lot of these workshops, the mix of audience is about maybe 30–40% industry people. The rest are from academics and academic institutions and government labs. So it's a nice mix, so they get a chance to talk to each other to find out about what are the concerns from the industry side. So in summary, industrial activities have always been an important part of IMA's mission. Our experience shows that this close collaboration with industry is a win-win for both the companies and the mathematical science community. IMA offers a program that trains students and postdocs interested in careers in industry and interested in finding out what industrial work is all about. The reputation that IMA has earned in industry took a lot of work and dedication, and much credit goes to my predecessors. I'm only doing more of what they had done, especially this visionary director from two predecessors before me, which is Abner Friedman. And I think that's all I have. Thank you very much for listening.